Then let's move to the next page, which is about this impact. Central impact. We can talk about these two, the central impact and oblique impact. Okay. And first, when we focus on the simple case, central impact is the velocities are along the line of impact, or which is the line through the mass centers. Okay, so when these two particles, they crash like that, then we can define this as the line of impact that is connecting the two dots, which is the mass centers like that. And perpendicular to that, it's called the plane of contact. And if we think about the forces or the impulse, we can have these two forces for A and B particle, which is negative P integral of P dt, and it's positive integral of P dt. P is the force. And we can think this is the effect of B on A. That's, this guy is, pushing this particle A. So this force or impulse is coming from B, okay? That's the reason, but it is acting on this particle A. So that's the reason why I have this point of application within this particle A, okay? So for this kind of impact cases, we can use those 3 to 4 step thing. First, always think about the axis that you select, okay? That's the first step for all the cases. In order to set this axis, you need to kind of think about how this is going to move, right? So from there, your physical, insight come in. So first, you select your axis, and then you draw the free body diagram. Draw the free body diagram, or just analyze all the forces like that. And then we apply this conservation of linear momentum. And we can also use the principle of impact and momentum. So we're adding more tools into our arsenal to analyze something. And for the conservation of linear momentum, that guy was what? It was, we have 2 particles here, right? So MI VI1 equals summation of all the linear momentums MI VI at time 2, right? Or if we write that out, because we have just 2 particles here, it's MA VA1 plus MB VB1 equal MA VA2 plus MB VB2. So The left-hand side is for time 1, and the right-hand side is for time 2. Okay, so you can define whatever time, but generally it's obvious. You want to define the time right before these two collide, and you want to define time 2 right after they crash to each other. Okay, so the linear, the summation of these linear momentums are going to be the same. And this thing is what we're going to learn today. The principle of impact and momentum is actually, we want to talk about this coefficient of restitution. So that is generally, we generally utilize this E, and E is a ratio VB1 minus VA1 VA. I think I made a typo here. Yeah. Sorry, I mean there's a typo. So VA1 VB1 VB2 minus VA1. Okay, so I need to update my notes here. Okay, so this is the ratio between the two relative velocities. Top one is separation velocity, and this is relative approach. Okay, so this coefficient of restitution is, sorry, there's another typo. This is 2, right? So this is for time 2, and this is for time 1, all right? It's when they are approaching to each other, the relative velocity when they are separating from each other, okay? That ratio is the coefficient of restitution. And we can very easily think if E is 1, that's the perfect, it's a perfect restitution, right? The speed they're approaching to each other, the speed they're separating, they're the same, right? So there's more like no energy loss or anything like that. And it's called as elastic impact, okay? So this case, no energy lost. And that means the magnitude of relative separation velocity is same as the relative approach, or OACH velocity. So you don't lose any of the velocity terms when they separate from each other. See what I'm saying? Like when they're approaching to each other, say that velocity was 10 meters per second, then when they bounce back and they separate from each other, it's 10 meters per second as well. So there's no energy loss, and that is kind of the perfect case, elastic impact. And plastic impact is the very opposite case of that, where E equals 0. And this thing is particles stick together. In other words, the relative separation velocity is 0. Because you can think about it, these two are coming to each other like that, and then once they collide, they become like a single particle. They stick to each other and they move to the left or right, depending on the situation. And there's no relative velocity between those two because they're going to be the same single particle, okay? So that is the plastic impact, okay? So particles stick together and there's no separation at all, okay? That's the plastic case. And things between these two are going to be, you know, the typical things. Steel, on a steel, the restitution ratio is going to be about 0.5 to 0.8-ish. Wood on wood is going to be 0.4 to 0.6. And glass, on glass, it's very interesting. It's close to an elastic impact. And tennis ball, it's generally about 0.7, and a golf ball is generally going to be 0.85. Okay, so this thing here is a little bit confusing. The A1, B1, A2, B2. So because it's a ratio, if you're not, you know, sure about whether this has to come first or VB1 has to be coming first, well, the actual definition is this, but you can also flip these together like that as well in some cases, like VB1 minus VA1 over VA2 minus VB2. It's going to be the same because, you know, you have a negative sign, and negative, they go away. So this one and that one is going to be the same. So one thing you want to make sure is these two are crossed to each other, and B, they are crossed to each other like that. A and A are crossed to each other. But you don't want to make a mistake. The later time, or the separation, is going to be this is the numerator, right? The other one is the numerator. Is that right? Yeah. So you want to have your separation velocity on the top and the approach, or the original velocity, that thing at the bottom. So you cannot switch these two up and down, but you can switch these two left and right as far as they are crossed to each other. So B and B, A and A. Okay, so that's a small tip that I can give you guys. And so what's happening to these typical things? Where's the energy going? So the energy is loss due to heat or sound or localized deformation. Okay, so typically there is a small energy loss, and that is making these not bouncing back perfectly. Okay, so we can think about this case. When this thing kind of falls, if it were a perfect elastic material, it's going to bounce back exactly to the same height. But because there is some loss, it's bouncing back to a height that is less than that. and it's bouncing back to a height that is less, bouncing back to a height that is less. Okay, so things like that happens here.